about waves and how light acts like a wave, and you were supposed to use the speed of light equation, and we talked about electromagnetic radiation and spectroscopy and all of that stuff. So we talked about this in Chem 1, how Einstein was able to show that light or electromagnetic radiation, it acts as particles. He called them photons, and you can show that the energy of a photon, which this is that energy equation that we had yesterday, what he did was he combined both equations together, where he took the speed of light, solved it for frequency, so that would be the speed of light divided by the wavelength, and plugged this in to right here to come up with this equation. Now, it would be really nice to just have that equation, and if you look in the solutions manual for some of the homework problems from 311, they just use that equation, but on the equation sheet, you are not given that. You were given the two separate, so that's why I only gave it to you separately yesterday, okay? But it does combine both of them. And from his findings with the photoelectric effect, he found that the frequency of light varies, and you're able to come up with a specific threshold frequency, where if you are below the threshold, then when you shine light onto a metal, no electrons are emitted. And this all it correlates directly with our EMR spectrum and how we talked about like what is the lowest wavelength of color and what is the highest wavelength of color that we talked about yesterday. But if it's lower than the threshold frequency, you won't emit electrons. If it's greater than the frequency threshold, then it will emit, and then the amount of electrons emitted increases with the more intense light. So for light with a frequency greater, the kinetic energy also increases linearly with this frequency increasing. So these were all his findings. With this, though, this is a picture of what his experiment was. So remember yesterday we talked about the rainbow and how the red is on top because it has the longest wavelength, and it correlates directly with the energy, longer wavelength, more energy. Or lower energy, sorry, and then a higher wavelength or a shorter wavelength is high energy. So if you have red light shining on a metal surface, it does not emit electrons, and that means that it's below the threshold. So it doesn't have a high enough threshold. Spelling. It doesn't have enough energy to push out the electrons. But this is blue light, and so blue light has a smaller wavelength and it's higher frequency, so higher energy, and that is able to shoot off electrons. And so that's what he did to figure this all out with his experiment, the photoelectric effect. Relating this to his his theory of relativity, the E stands for energy, M stands for mass. See, this is the speed of light. You can change this inserting wavelength into what we call the de Broglie equation, which we found yesterday that this is the equation that you need, I think, for number 56. So technically, you haven't done 56 yet. For whatever 311 homeworks were, then that's fine because you're going to use this equation for it. In this equation, M stands for mass, and you need the mass to be in kilograms for everything to work out perfectly. The H is still the 6.626 times 10 to the negative 34 that we had in the regular E equals HV equation. But then instead of being frequency in the de Broglie equation, this is actually velocity. So usually with the velocity and with with SI units, the velocity needs to be in meters per second. Okay, so when it says to solve for velocity, you're going to be solving for meters per second. So let's use that equation. Compare the wavelength for an electron that has a mass of 9.11 times 10 to the negative 31 kilograms, traveling at a speed of 1 times 10 to the 7th meters per second, with that of a ball that has a mass of 0.10 kilograms, traveling at 35 miles per hour. I don't play baseball. Is 35 miles per hour throwing a ball like slow, fast? slow. Okay. I always remember like seeing like pictures and stuff, and they like show like 90 miles an hour. That's fast. Okay. Okay. That's miles per hour though, and this is meters per second. So it is different. What? Sorry, just thinking. I don't know, but it's meters per second, so it might be fast if we're thinking miles per hour in our minds. Okay, so what we're going to do is we're going to use this equation. And we're going to do it first for the electron, and then we'll do it again for the ball, and we'll compare to see how are their wavelengths different, or how are they the same. Okay, so for the wavelength of the electron, so this is just E negative for electron, okay, I'm just labeling my wavelength. It's the 6.626 times 10 to the negative 34 over 9.11 times 10 times 10 to the negative 31 times 1.0 times 10 to the 7th. I think I said it wrong, so I apologize. So I plugged in the mass for M, plugged in the velocity for V, and then H is that constant value. It should be pretty small. What do you think the unit is going to be on wavelength? If you look at our units that we have, we plugged in a kilograms, we plugged in a meters per second, and the constant is just like a whole bunch of crazy units to make everything cancel. So do you think, what is wavelength? Is wavelength like a time amount? Is wavelength a length amount? Is wavelength a mass amount? What do you think it's going to be? It's a length. So what length do you think it'll be? Meters. Because of the meters and the velocity. Okay? So now we're going to do the same exact thing, but we're going to plug in the information about the ball. So for the ball, I'm just going to put the wavelength of V for ball. Okay? We'll still use the same constant, 6.626 times 10 to the negative 34. And our mass of the ball is 0.10 kilograms, which is like 100 grams. And the velocity is 35 meters per second. I feel like 35 meters per second is pretty fast. Yeah. Because the meter is about a yard. To travel that distance 35 times in 1 second, it's probably pretty fast. So maybe it is the picture throw. Just, we need to convert it to miles per hour to know if it is or not. Maybe it's fast. Okay, so what'd you get? Did you get times 10 to the negative 34? Okay, and this will also be meters because our velocity also has meters in it. Okay, so what does this mean? You're supposed to compare them, right? Which one's smaller? The ball's wavelength is a lot smaller than the electron's wavelength. The electron's wavelength is short, but what this leads for us to prove is what's called diffraction. And that's because if you were to take this value, it would relate to wavelengths that you see between atoms in a crystal. So this is just proving what our next thing that we're going to talk about is called diffraction. This results when light is scattered from a regular array or points or lines. So have you ever, this old-fangled technology, this is a CD up here, where they're just like moving it so you can see the rainbow of colors, so it's just scattering the wavelengths of light. Also, looking through a prism is also a way to scatter light. So diffraction results when you scatter the light from a regular point or line. And so the visible light wavelengths are not scattered in the same way, which is why they separate, making the rainbow effect when they're passed through a prism or shown off of your CD. When they are separated, then two things can happen, creating what's called a diffraction pattern. They can either constructively interfere or they can destructively interfere. Okay, this picture is found on your textbook on page 304. And it is, this picture right here is called a barrel crystal. So what they did was they had a crystal, whatever a barrel crystal is, I don't know what it is right now, but then they passed light through it, and this is what they saw. Okay, so the constructive interference means that they're in sync with one another, and so the wavelengths will just add, making it to be a bigger peak and a bigger trough. Okay, so I know it's kind of small to see in the back, but the two are in sync, so then they just make it to be bigger. Where destructive interference is when they're opposite each other. So the trough is going towards the peak of the other one, and they go up and down like that. And so what happens is if they're going oppositely from each other, they just cancel each other out. So the dark spots in this picture show where there is destructive interference, and the really bright spots, like the really big spots, are showing the constructive interference, where the light is building on top of each other, making it more visible for us to see. Okay, so these two different types of patterns, and when we pass light through different crystals of elements, helps us to realize that light does move in terms of waves. So even though we know that there's particles, and we know that with the particles there's certain amounts of energy, they do have the wave-like characteristics still. And so this is just another way to prove, on top of what Einstein did with the photoelectric effect, how all matter has particulate and wave properties. Okay, so this just goes into more detail, trying to explain that kind of thing for us. Okay.